Swayamprabha. Digital India. Educated India.
Greetings and welcome again to this course on CFD. In this module, we are going to talk about discretization of convection term and diffusion term in detail. Last class, we listed algorithm steps to do the test case problem of flow in a lid driven cavity, grid generation, discretization of the governing equation, solving the momentum equation to obtain intermediate velocities, solve the pressure Poisson equation, project the intermediate velocity on a divergence free space using the pressure obtained from the pressure Poisson equation, repeat the process till the convergence is obtained. Once you get solution, then we do post processing. So, in this particular module, we are going to talk about two steps 2 and 3, that is discretization of the governing equation and solving the momentum equation to obtain intermediate velocities. As we did in module 1, in this module also we will show corresponding code and explain each step. The governing equations are discretized on staggered grid. We mentioned in the last module we have 3 options: staggered grid, collocated grid and semi staggered grid. Collocated grid results in oscillation, hence we go for staggered grid, and we are using finite difference method to solve the equation. The staggered grid arrangement is shown in the next slide. U velocity nodes are present on the vertical faces and V velocity nodes are present on the horizontal faces. Then pressure is stored at the center of the cell, and this is a schematic to explain what is a staggered grid. So, we have vertical thick lines as I am showing here, then you also have a dashed vertical lines as I am showing here. Then we have horizontal thick lines I am showing now, and in between two horizontal thick lines you have a dash horizontal lines as I am showing here. And this is staggered grid arrangement for finite volume procedure. So, U velocity is stored as shown here. This is a U velocity, this is the finite volume cell for solving U momentum equation, and this is the finite volume mesh for solving V momentum equation, and pressure or any other scalar is stored in this finite volume mesh. So, as you can observe, U, V and pressure are stored at different location, that is why the name staggered grid. Now, for the problem that we have considered, we are following finite difference procedure. Hence, for that finite difference procedure and for the problem, the staggered grid arrangement is shown here. We have I, that is grid lines in the x direction running from 1 to I is equal to I max. We define 4 grid in x direction. So, 1, 2, 3, 4 vertical lines. Similarly, 4 horizontal lines for grid in y direction. So, we have 1, 2, 3, 4, and that is running from j is equal to 1 to j is equal to j max. Because it is staggered, we have U velocity which is shown here by a triangle, and V velocity which is shown by a circle, and pressure at the center of the cell which is shown by into mark. So, you can observe in finite difference procedure for staggered grid, velocities, how the velocities are stored. U velocities are stored on the vertical face, V velocities are stored on the horizontal face, and pressure is stored at the center of the cell. We have defined 4 by 4 mesh arrangement, and that results in 9 cells. Now, we have defined boundary conditions in two different forms. You can have a Dirichlet type of boundary condition where you use primary variables, and you can have a Neumann type of boundary condition where we use pressure. Now, to apply the boundary condition, we need to have what is known as a ghost cell, that is cell beyond the actual computational domain. So, what is shown here is for y direction, the thick black line is the actual grid arrangement. So, 3 by 3, then we have a ghost node defined extending the domain. So, we have a red color, that is a ghost line. So, J is actually J max plus 1, because J max is actually the last horizontal black color line. Now, we define one more ghost node in y direction on both the sides. So, one on the upper side J is equal to J max plus 1, another one on the lower side where it is beyond this J is equal to J 1. Okay. So, this is shown by the red color. This is required to apply the boundary condition. So, use staggered grid with the ghost cell for boundary condition implementation. So, number of u velocity unknowns becomes I max, because we do not have any extra line in the I direction. When you solve u momentum equation, we have only extra in j direction. So, that is J max plus 1 is considered. Number of u velocity unknown becomes I max into J max plus 1. Similar arrangement for V cell, we will look into that when we do V momentum equation. And this is the code snippet which actually does what we have just now explained. Nx is the number of cells in x direction, Ny number of cells along y direction, and we have a variable declaration. P is for pressure. Now, we define array size for the P zeros, I max plus 1 and J max plus 1. So, pressure unknowns are Nx plus 2 into Ny plus 2, including ghost nodes, because when you come to pressure, it is appearing in both the equation. So, we have a ghost node appearing in x direction as well as in y direction. Then this is RHS P is in the pressure Poisson equation, you have a source term on the right hand side, and that is what is defined here as RHS, and they are again initialized with the zeros of I max plus 1 and J max plus 1. Then we have to calculate divergence, and that is also stored. Vertical velocities are actually V. So, V star is a temporary velocity which is the first step in the projection method. So, V stars are defined zeros I max plus 1 to J max, and V is actual velocity again defined as zeros I max plus 1 and J max. So, V is a velocity unknowns, this is with Nx plus 2 multiplied by Ny plus 1, because when you solve V momentum equation, you require ghost nodes in other direction. So, that is why it becomes Nx plus 2 and Ny plus 1 is number of nodes available in the y direction itself. Similarly, for u velocity, which is otherwise horizontal velocity. So, u star and u, they are also defined with array I max and J max plus 1 and I max J max plus 1. So, you can observe here for V star it is I max plus 1 and J max, for u star it is I max and J max plus 1. This is for intermediate velocity and u velocity, and when you solve u velocity, then we have a ghost node defined in the other direction. So, it becomes Nx plus 1 star Ny plus 2, it is a number of minimum required array size. We follow the projection step method. So, momentum equation is solved without considering the pressure term. Momentum equation is discretized in the following manner. We will explain first with the help of u momentum equation. The procedure is same for v momentum equation. So, u momentum equation after neglecting pressure term is written here. We need to discretize, and the discretized equation is as shown here. So, it is explicit, we already mentioned. So, we have all the known quantity with a superscript n, only unknown is star quantity. So, u star minus u n by delta t, and all the knowns are taken to the other side as shown here, where u is a velocity vector, of course, it is for v also it is included. Consider the u momentum equation. The above discretized equation is written specifically now for u momentum equation as shown here. Now, there is one small difference between the first equation and second equation for convection term. This u n can be taken inside the partial derivative, and that is written here as dou by dou x of u n square. You can actually perform this operation, that is dou by dou x of u n square, you can write it as 2 u n dou u n by u x and other term, and one term actually goes to 0 because of the continuity. So, it is possible to write a convection term in different form, and one form is as shown here. This is for convenience because u is defined at one location. So, anyway you can take it into the part inside the partial derivative, and any additional term which is coming because of this partial derivative inclusion will go to 0 once you satisfy the continuity, and V n again is taken to the other side as shown here. So, if you do the partial derivative for both these terms together, you will have one extra term from the first term as dou u by dou x. Similarly, one extra term from the second term as dou v by dou y. If you sum them up, it is actually the continuity, which is actually 0. Consider first the diffusion term, that is the second term here. So, it is written as shown nu dou squared u n by dou x squared plus dou squared u n by dou y squared, and nu is maintained. Now, we follow second order central differential scheme for the derivative, second derivative, that is what is shown here. So, for the first term in the bracket dou squared u n by dou x squared, the discretized equation is shown here. Because we mentioned it is explicit, we have all superscript n. So, u evaluated at I minus 1 j n plus u I plus 1 j n minus 2 times u at I comma j n by delta x squared. Similarly, for the second derivative in y direction, and that is what is shown here. Corresponding code. So, we have memory allocation u star, alpha is minus dt by r e delta x squared multiplying delta y squared. Compute the explicit terms, diffusion terms are calculated here, and we follow staggered grid. So, we have a east, west, north, south terminology to be used here. So, u east and u west are calculated by taking the average of the velocities at staggered node points, because we want u at staggered location. So, for I equal to 2 to I max minus 1, and for j equal to 2 to j max, diffusion term I comma j equal to alpha star dy squared multiplying u I plus 1 comma j minus 2 times u I comma j plus u I minus 1 comma j. So, this first 3 terms in this particular bracket are for the first derivative dou squared u by dou x squared, second order central differential scheme for dou squared u by dou x squared. Because we have alpha defined as minus dt by r e delta x squared and delta y squared, we do not have a delta y squared, we are actually multiplying here alpha. So, that needs to be accounted properly, hence we have delta y squared multiplying the entire factor. Similarly, when you do the second derivative for y direction, that is dou squared u by dou y squared. We have only delta y squared, we do not have a delta x squared, whereas alpha is generically defined considering both delta x squared and delta y squared. So, extra delta x squared needs to be accounted properly. Hence, we have delta x squared multiplying the finite difference of del squared, finite difference of dou squared u by dou y squared, and as shown here. So, u I comma j plus 1 minus 2 times u I comma j plus u I j minus 1. So, this is actually central differencing, one is a point of interest and one on the right side, one on the left side. Next, convection term, we have u dou u by dou x plus v dou u by dou y, and we can rewrite convection term considering the u and v inside the partial derivative. So, the first term is actually dou by dou x u n squared plus dou by dou y u n v n. So, if you actually perform the partial derivative on the terms inside the bracket, you will get two additional terms, and those two terms together will go to 0 because of the continuity equation. Now, we are following staggered grid arrangement on finite difference procedure. So, we have a north east west south terminology coming into the picture. So, we have first term in the discretized form is shown here, u east n squared minus u west n squared by delta x, plus for the second term the discretized form u north at nth level, v north at nth level minus u south at nth level and v south at nth level by delta y. Now, what we have to be careful is we have to evaluate u at east, west, north and south, and they are done separately here. Now, we have to recall what we did in finite volume treatment on convection term. We say convection terms are nonlinear, that is u multiplying dou u by dou x. We need to evaluate u at phases and we need to get dou u by dou x at phases, and that is what is followed here. We explain three different procedure, that is pure upwinding, then central differencing type of approximation, linear approximation, quick approximation, hybrid type, etc. And what is shown here is a linear approximation or central differencing type approximation. So, u at east is u I comma j plus u I plus 1 comma j divided by 2. Similarly, for u at west and u at north and u at south, and for v also we follow the same, and that is from j direction. So, v at I j plus 1 and v at I plus 1 j plus 1 divided by 2. Similarly, v at south, v at I j minus 1, v at I plus 1 j minus 1 by 2. We explain all this in detail when we did finite volume formulation for convection term. Corresponding code snippet is given here. So, u for I equal to 2 to I max minus 1, for j equal to 2 to j max, u at east, u at west, u at north, u at south, v at north and v at south, all are calculated. Once you calculate, then you write the convection term for I comma j as explained in the discretized equation, and it is shown here. dx and dy are already defined, hence they are directly used. Now, we have dx and dy for simplicity's sake uniform and equal. If it is not uniform, then we have to take corresponding weightage, and dx and dy they will also be as a function of array. In the last slide, I mentioned about rewriting convection term. I did not explain at that time why or how it can be rewritten, and there is no change in the actual equation. This slide as well as in the next slide, I am going to explain in detail how the convection term can be written. So, u dot del into u is written as u into dou by dou x plus v into dou by dou y of u, dou u squared by dou x equal to 2 into u dou u by dou x equal to u dou u by dou x plus u dou u by dou x. So, 2 times u into dou u by dou x is expanded as 1 u into dou u by dou x plus u into dou u by dou x, and then dou by dou y of u v as u into dou v by dou y plus v into dou u by dou y. If you put these two together, then we get dou by dou x of u squared plus dou by dou y of u v equal to u into dou u by dou x plus v into dou u by dou y plus u into dou u by dou x plus u into dou v by dou y. So, we have 1 u into dou u by dou x and 1 v into dou u by dou y grouped separately as shown here. We rewrite that equation again as shown here, but in an incompressible flow we know the continuity equation for 2 dimensional flow as shown here, dou u by dou x plus dou v by dou y equal to 0. Hence, the rewritten form of the convection term, that is dou by dou x of u squared plus dou by dou y of u v is same as u into dou u by dou x plus v into dou u by dou y. Hence, there is no additional term introduced because of this rewriting. The u momentum equation, we follow explicit discretization. The computation of intermediate velocities become a simple substitutions, because we do not need to store, it is directly related to velocity component in the form of a discretized equation. So, u star minus u n by delta t equal to minus convection term plus diffusion term without pressure term. So, the left hand side convection term is brought to the right hand side and diffusion term on the right hand side remains the same. We follow explicit formulation, hence it is written as simple as shown here. So, u star equal to u n plus delta t into these terms. So, corresponding code is shown here for I equal to 2 to I max minus 1 and for j equal to 2 to j max. We calculate intermediate velocity, we use u star I comma j as u I comma j plus delta t. In the code we use dt multiplying convection term and diffusion term. N, once you solve equation, we need to ensure implementation of boundary condition, and that is applying boundary condition u star on the left wall u star 1 comma 2 to j max equal to 0, because we are following Dirichlet type of boundary condition. Using the primary variable, we mention u is equal to v is equal to 0 on all the 3 walls. So, we have a left wall, right wall, bottom wall, and the top wall we have a velocity specified for u. So, u star 1 to I max j max plus 1, that is on the top line grid line, is equal to 2 into velocity minus u star 1 I max and j max. In this module, we have seen in particular convection term discretization, diffusion term discretization, and we learn what is known as the ghost node cells in x direction and y direction when you solve respectively u momentum equation and v momentum equation for the implementation of boundary condition. We also showed corresponding code including the implementation of boundary condition. In the next module, we will proceed with some other explanation and proceed with in the next stage in the algorithm. Thank you.